We're going to jump directly into this 3.5. This is the last set of notes that we're going to go through. Tomorrow we're going to start reviewing. There is a gap in the notes from 1.4, if you guys remember 1.4b. I didn't get a chance to go through these additional continuity practice problems. But I'll just make this part of the review for tomorrow. This will be something that will be good as we prepare for the test, and we know what continuity is. We can adapt it for piecewise functions, and we'll start off tomorrow with this. I was hoping to squeeze this in, but based on previous periods, it's going to take me the full period just to do 3.5. So we have 3 days to review. So tomorrow, when we go through this, this will be part of our test review. So to begin with, I want to start off with just some basic knowledge of vertical asymptotes and horizontal asymptotes. We know how to distinguish them by looking at a graph, but are we able to distinguish them if we're looking at the limit notation? And I want to talk about that because they kind of look similar, and but subtle differences is going to tell us whether that limit statement is telling us about a vertical asymptote or whether that limit statement is telling us about a horizontal asymptote. So I think the easiest way to do that is let's just talk about the graph, see how it connects with the limit notation, and then hopefully if you're able to see this limit notation without the graph, you can still make some good observations about horizontal asymptote and vertical asymptote and visualize what this could look like. Now, if you look at this graph here, this is a rational function. I got the dotted lines representing the vertical asymptote, and I also have a dotted line representing the horizontal asymptote. So this vertical asymptote, okay, let's do the limit as we approach the asymptote. So here we're approaching 2 from the left side of 2. What this is saying is that I'm going to pick a point to the left of 2. So that's here. And I'm going to move towards 2. So I got to move to the right. So I'm going to create an arrow to indicate that I'm moving to the right. And if you see this, as I approach my asymptote, my y value is going towards infinity. So I'm going to represent my one-sided limit as we approach this vertical asymptote. For this statement, limit as x approaches 2 from the right side of 2, that means I'm going to pick a point to the right of the vertical asymptote. So I'll just choose a point close by. And I'm going to follow the arrow or follow the graph as we approach 2. So I'm going to move to the left and follow along the path of the graph. This is going down to negative infinity. So as we get closer towards 2, it's going down to negative infinity. So, okay. So if we approach a real number from the left or from the right, and the result that we get is either positive or negative infinity, we know that we're dealing with a vertical asymptote. Okay, approaching a real number, but limit is undefined / positive or negative infinity. We need to be able to look at this in the future and just recognize that this is talking about the vertical asymptote, and you should be able to sketch some version of the graph that kind of resembles this, right? Maybe things slightly to the left, to the right is not quite the same, but just based off of the statement, you should be able to create something that looks like mine. Right? Maybe the arrows are, maybe this branch is higher up, maybe this branch is lower down, but the arrows should be consistent with my dotted line. Okay, so that's vertical asymptotes. With horizontal asymptotes, it's more about the end behavior. Okay, so here you see there's a horizontal asymptote here, right? Now this horizontal asymptote is for this part of the graph. Okay. It doesn't apply on the left side. Now let me talk about this notation here. Limit as x approaches infinity. What this is saying is that if you're approaching infinity, what you're going to do is you're going to pick a point at the right edge of your graph. So I'm going to pick a point relatively close to the right edge of my graph, right before my graph exits to the right. But once I identify that point, I'm going to draw an arrow towards infinity. So I'm going to move towards infinity. So I'm going to I'm going to follow the path of the graph to the right. As I follow the path of the graph to the right, I see that my y value is kind of flattening out, right? It's getting closer towards this dotted line, and that indicates that we're dealing with the horizontal asymptote. Our graph is getting closer towards this horizontal line. It'll never reach it, but it'll get infinitely close to it. So there's a horizontal asymptote at y equals 2 for this portion of the graph. Likewise, if I ask you find the limit as x approaches negative infinity, what you're going to do is you're going to pick a point on the left edge of your graph. And you're going to exit the graph to the left and follow the path of the graph as it exits to the left. And here, if I follow the graph to the left, I see that the way that my arrow is pointing, it doesn't show that it's flattening out. So we're going to assume that it's going to keep rising and rising. This dotted line has no impact, doesn't describe anything on the left side, it only describes what's on the right side. And so we say that this limit doesn't exist, but we have a more specific form, which is positive infinity. So we call this end behavior because we want to know what is the behavior of the graph as it exits out of our view. Now notice the distinction between horizontal asymptote versus vertical asymptote. For vertical asymptote, where x is approaching a real number, but the limit is infinity or negative infinity. But horizontal asymptote is kind of flip-flopped. We're approaching infinity or negative infinity, and the limit is going to be a real number. That's when we know we have a horizontal asymptote. So look at the placement of the x and y values. Okay, flip-flop, right? Real number is here, infinity is here. Okay, so I wanted to kind of give us or start off with some visual foundation before we build on this as we go into chapter 3.5. Any questions with this? Are we good with the notation matching up with the graph? Or if I didn't give you the graph, you should be able to create something that still has these properties, that's going to resemble my arrows in those 4 spots. Okay, 3.5 notes. This is limits at infinity. We're dealing with end behavior. So anytime we see anytime we see this notation, these notations, we know that we're looking for potential horizontal asymptotes. Okay, so here's the first scenario. If we're approaching infinity, well, let me read this statement here. If f of x equals p over q, then if we want to find horizontal asymptotes, we compare degrees between the numerator and denominator. Okay. Example 1. Okay. We see a limit, we see an algebraic expression. Okay. What do we say from previous days when we're dealing with limits algebraically? What's the first thing that we always do if we're approaching a real number?
Plug it in.
Plug in, right? Plug in that whole number integer, no decimals, right? If it's a 3 from the left, we plug in 3. If it's 3 from the right, we plug in 3. If it's 4, we plug in 4, right? So whatever number, we do a direct substitution. But that is for real numbers, okay? Infinity is not a real number, so we have a completely different set of rules for infinity. So I want us to make that clear in our heads. If you see a real number, plug in that whole number. Don't get distracted by a one-sided limit. If you see infinity, we have a completely different set. Okay. And the new set of rules that we do for infinity is we compare the highest degree of the numerator versus the highest degree of the denominator and see which one is higher, which one is lower, or whether they're the same. So this first scenario, we see that the numerator has a degree of 2, denominator has a degree of 3. The numerator is less than the denominator. So whenever we see a denominator being the higher degree, then our horizontal asymptote is always going to be just 0. Okay. Let me talk about why that's the case. Okay, the reason why that's the case is imagine your value getting larger and larger. Let's say you plugged in 1, then 2, then 3, then 100, then 1,000,000. Okay. Your numerator and denominator, they're both increasing, but your denominator is going to be growing at a faster rate than the numerator. And if your denominator is growing at a faster rate than the numerator, your overall fraction is going to get smaller and smaller and smaller. And the pattern is that it's headed towards 0. It's never going to reach 0, but it will get infinitely close towards 0. Let me just give a side example here. Let's say I had 1 over 10 versus 2 over 100 versus 3 over 1,000 versus 4 over 1,000,000. You see how in both instances, my numerator and denominator are both increasing? But it's obvious that my denominator is growing at a much faster rate than the numerator. So look at the overall fraction here, 1/10 versus 2 over 100 versus 3 over 1,000 versus 4 over 1,000,000. Okay, these fractions are getting smaller and smaller and smaller, and it's headed towards 0. That is why whenever your denominator is rising at a faster rate than the numerator, your limit as x approaches infinity or negative infinity is going to be 0. Okay. So this applies for negative infinity as well. Visually, right, if my asymptote is here at 0, it doesn't matter if I'm approaching to the right or to the left, my end behavior is still going to be the same. They're both going to be approaching 0 if my denominator is higher than the numerator. Okay, let's look at the second scenario. If we're doing limit as x approaches infinity, like we are here, if the denominator and numerator degree are the same, then the horizontal asymptote is just the ratio of the numerator and denominator coefficient. So here, if we compare, numerator is x squared, denominator is also x squared. So if my degrees are the same, they're both rising at the same rate, but the 5 and the 2 is what is determining the exact horizontal asymptote. So we just take the ratio of the coefficient 5/2. So maybe the graph looks like this. Here's 5/2. Let me give a related scenario here. Oh, sorry, squared. Again, degrees are the same. We just take the ratio of the coefficients, so also 5/2. Okay. It doesn't matter if we're approaching positive or negative infinity. It's just the ratio of the coefficients. Okay, so maybe this is what the graph looks like, right? Here's 5/2. If I'm moving to the left, same asymptote as if I'm moving to the right. Maybe it's coming from different directions, but it's going to level off at the same y value if my degrees are the same. Now, students tend to make mistakes with this problem. So I want you guys to guess. What do you think is a common mistake that students make that causes them to not get the right answer in this situation? What do you guys think?
Dividing the degrees instead of the coefficients.
Okay, divine degrees instead of the coefficient. There's something that throws students off about negative. Yeah, I think the tendency is students sometimes see this and it's like, oh wait, I see negative infinity, maybe I got to do something different with this, so I'm going to make that a negative 5/2. Right? We don't change the signs. Okay, don't change the signs. Okay, it's just the ratio. Don't overthink it. Don't overdo it. But also visually, right? If it's 5/2 and negative 5/2, what that's saying then is that we're going to be seeing split horizontal asymptotes. And we usually don't see that, right? There's not many graphs that we can think of where we have split asymptotes on either side. Usually it's just one asymptote and either it's getting closer to it or it's not. So if both are getting closer towards it, it's going to be towards the same asymptote. So if your degrees are the same, if you're dealing with a rational function, there's only one asymptote. Doesn't matter if you're moving to the right or to the left, it's just the ratio. Don't try to change the sign. Okay. This negative throws off a lot of students here. Okay, third scenario. Again, limit as x approaches infinity. We look at the degrees. Numerator here is greater than the denominator. So what that's saying here is that if my numerator is growing at a faster rate than my denominator, then this overall fraction is getting larger and larger towards infinity. But when we talk about infinity, we have two options, right? Our two options, the limit doesn't exist, but we have two options. It's either rising to positive or it's falling to negative infinity. Now, the way that we're going to decide between these two options without looking at the graph is I'm going to find a point. I'm going to find just an arbitrary number for me to test that is in the direction of infinity, and I'm going to choose a rather large number that is outside the view of my coordinate plane. So I'm going to test 100 because that is in the direction that I'm headed towards. And it's kind of an arbitrary number. I guess you could test 10, but I think 100 is kind of it's like a safe large number that we're going to get a safe read of our graph. So I'm going to plug 100 in for x, and I just want to test the signs, right? I already know I'm choosing between two options. I just want to know which one of these to choose from. So plug in 100. And I don't care about my lower degrees. My lower degrees is not going to have an impact. It's just my highest degrees. Numerator gives me positive. Denominator also gives me positive. So it must be positive infinity. Let me give a related scenario. Limit as x approaches negative infinity. I'm approaching infinity, or in this case, negative infinity. I know I got to compare degrees. My numerator is winning out over my denominator. I know I'm down to two choices. But now I want to choose a number in the direction that I'm headed towards. I'm exiting the graph to the left, and a large number or a large representation of that movement towards the left is negative 100. So I like to just numerator gives me negative, denominator gives me positive. Negative over positive is negative, so negative infinity. Okay, if the degrees match, you don't do anything. It's just a ratio. Okay, there's not a separate procedure for positive and negative infinity if the degrees are the same. But if the degree of the numerator is greater than the denominator, we do have to make some adjustments because we're having to choose between two options, and whether we're moving to the right or to the left, that's going to create more options for us to choose from. So we're either testing 100 or negative 100, depending on which direction that we're headed, so that we can choose between our two options, either positive or negative infinity. Okay, so maybe the graph looks like this, right? And we want to determine whether these arrows are pointing without the use of a graph. So we find the limits. Once we realize that there is no horizontal asymptote, we go about testing a number that's appropriate for our problem so that we can determine between the arrows going up or going down. All right, let's see if we can practice through these examples and see if we can see if these scenarios make sense. Okay, limit as x approaches infinity. We know we're dealing with infinity. We know that we're comparing degrees. We don't plug anything in, right? There's not a real number, so we don't follow that procedure. Okay, we compare degrees. Numerator is winning out. So same scenario as third scenario, right? Choosing between positive or negative infinity. Look at where you're headed towards. You're headed towards positive infinity. You want to pick a number that is to the right as we exit the graph to the right. So a number that we can use that is safe is 100. We get positive over a positive, which is positive infinity. Okay, limit as x approaches negative infinity. Compare degrees. Again, numerator wins out. We want to choose a number in the direction that we're headed towards. We're exiting the graph to the left. So a number that represents it is negative 100. So I get a positive over a negative, which is negative, so negative infinity. Okay, number 6. Approaching infinity, sorry, negative infinity, we know we have to compare degrees. What do you notice about number 6?
The same.
Same. So we take the ratio of the coefficients, so what would your limit be?
Three over 2.
Okay, which one is it? Is it 3 over 2 or 3 over negative 2?
Just 2.
We're going to have to keep that negative. Okay, so this negative is going to impact our coefficient. Okay. Wait, do we need to do anything with that negative infinity? Do we need to make an adjustment because it's negative infinity?
No.
No change. Okay, so I want to keep reminding us, okay, no change. I know that's distracting, but no change. Okay. Number 7, approaching infinity, same expression, same answer. Doesn't matter if we're moving to the right or to the left, there's only one asymptote, and that asymptote is going to stretch from one end to the other. Yeah, careful with this. This is, yeah, easy mistake to make. All right, number 8. Infinity, we compare degrees. This is the easiest case, right? Your denominator is higher. We know it's always going to be 0. Okay, number 9. We're approaching negative infinity. Compare degrees. Okay, numerator wins out. The way we decide which way to test, we're exiting the graph to the left. And as we exit the graph to the left, a large number that we can choose in that direction is negative 100. And we're just testing so that we can decide between our two options. Numerator is negative, denominator is positive. Negative infinity. Any questions with procedures and steps? So I just want to stress how important it is for us to know what category we're dealing with. So right now, it doesn't seem too hard maybe because you're seeing these are all infinity. But once we start mixing real numbers with infinity, we got to be really clear what our first step is, right? If we don't have that two categories in our heads, real number versus infinity, that's going to throw us off. We're not going to have like a anchor to stand on. We're going to just be kind of guessing our way through our steps. So I want us to be very clear that, you know, if you see infinity versus real number, you got to know what the first step is for either type. If you can, and I think that first step is so important, right? Once you get that first step down, then everything kind of falls into place. But determining that first step for limit problems is, you know, where a lot of the challenge is, especially if there's a mixture of different types next to each other. Okay, any questions here? All right, let's go to the back. Finding horizontal asymptote with radicals in the denominator. This is a very special case here. This is not common at all, okay? At least not with what we have to see. But we're including this type of a problem because this has shown up on the AP exam, so want to make sure that that we're exposed to this, so we'll know what to do when we come across it. The reason why this is a strange and not a common case compared to our other problems that we're going to see is that in this type of a scenario where you have a linear over a square root of x squared, it has to look like this. It has to have this specific relationship, okay? It's so unique. It's, you know, very specific. But in this scenario, we're going to have a graph that actually has a split asymptote, split horizontal asymptote. As we move to the right, okay, it's going to be a different asymptote than if we move to the left. Okay. This is not a common type of a problem, but we're going to kind of talk through it. So the way that we can identify, so once we look at this and we realize, okay, I'm dealing with the split asymptote, I'm looking for two different asymptotes. And the procedure that we have to follow is that we're going to have to find the limit separately. Once for moving to the right, and then the other for moving to the left. Okay, so let's think about the procedure that we took on the first page. Infinity, we know that we don't plug in numbers, we're going to compare degrees. So tell me, what is the degree of the numerator that you see?
1.
1, okay. I'll put a 1 here. Now look at the denominator. What is the degree of the denominator?
1.
Also 1. And maybe some of us are thinking, wait, I see an x squared there, so why is it not x squared? Well, you got an x squared there, but then the square root is kind of undoing that x squared, right? That square root of x squared is bringing it back down to an x. So what do you notice about the degrees?
They're the same.
Same, right? And how do we handle same degrees for infinity? We take the what?
Coefficient.
Right, ratio of the coefficients. Okay, all right. So let's keep going with that thought, thought process. The numerator has a coefficient of 3, right? That's pretty clear. What is the coefficient of the denominator variable?
Is it 2?
Yep, that's right. This 4 is inside the square root, so we have to take that into account when we build our coefficient. Root 4, the principal value of a square root is always positive. So this is 3/2. As we move to the right, our horizontal asymptote is going to be 3/2. We can see in this picture here. Okay, any questions? We're kind of taking what we learned on the first page and kind of adapting and adjusting to that strange denominator setup there. Okay, let's look at the negative side of it. Negative infinity, again, we're comparing degrees, same problem, so same ratio, right? 3 over square root of 4, which is 3 over 2. But there's something different about this negative infinity. Okay. Now, this negative infinity, it's going to have an impact on the numerator, right? Positive infinity, negative infinity is going to have an impact on the numerator. But this denominator, it's going to be stubborn in the sense that it's always going to stay positive. Doesn't matter what number I plug in, this denominator is always going to stay positive. So only the numerator is changing the sign. Denominator is not changing the sign along with the numerator. So what's going to happen is that it's going to create this issue of a different value, a different asymptote. And it's always going to be the opposite sign of what we started with. I know the first page I kept stressing that if the degrees are the same, we don't change the signs, right? I just got done saying that. But this is a special case, right? This is a strange case that square root is throwing everything off and it's causing a different sign to appear. So I want you to think of this as the exception to the rule. This is not the norm, okay? The norm is rational functions where you have no square roots in the way. It's x squared over x cubed. We don't change anything there. But the exception to the rule is when there is a strange looking graph with split asymptotes. That's why we get this scenario. So we say this. We say that horizontal asymptote, okay, are at y equals 3/2 and y equals negative 3/2. So once you find one, you have the other. Just have to know that they're going to be opposite signs. Comparative growth rates. This is the last topic here. Families of functions, okay, will grow at predictable rates in relation to each other as we approach infinity. So as we approach infinity, if we have a numerator and denominator, and the numerator and denominator falls under these specific families of functions, we're going to be able to find a limit based off of these relationships. So the slowest function is logarithms. So anything like natural log of x, log base 2 of x, right? Any log form is going to grow at the slowest rate, followed by radicals. It could be square root of x, could be cube root of x, okay, any radical. And then next is the x squared. That's the parabola. Any polynomial. And then finally, the graph that moves at the fastest rate or grows at the fastest rate are the exponential functions. So it could be e to the x, 2 to the x, 3 to the x. Okay. So here is what we're able to conclude quickly if we understand these relationships here. Let's say I had limit as x approaches infinity. and I have a distinct family of function above, and then another distinct family of function below. And we realize that the denominator has a function that's growing at a faster rate than the numerator, then what's going to happen is that this fraction is going to get smaller and smaller and smaller, and your limit is going to be 0. Okay. Likewise, if I have limit as x approaches infinity, and again, there's no negative infinities here, this relationship only works if we're moving to the right, if we're going to positive infinity. It doesn't work in this negative region here. Let's say we had the faster function up top, or the faster growth up top. Then what's going to happen is that because our numerator is growing at a faster rate than the denominator, your fraction is going to get larger and larger and larger, and there's only two options. It's either positive infinity or negative infinity. And the way that we can test is, because we're always moving to the right, we can always test 100. Okay, a few minutes. I'll see if I can squeeze in some of these examples here. Okay, limit as x approaches infinity. Again, this only applies if we're moving to the right, doesn't apply when we move to the left. If we try to compare degrees like we normally would if we see infinity, we see an issue, right? Okay, there's not really a degree for my numerator because this is not a polynomial. I don't have a degree for this numerator here. So we got to maybe think, okay, maybe it's maybe these are different families of functions I can compare between. So the numerator, what family of function does that fall under?
Radicals.
Is a radical, right? So I have a radical over x squared. X squared falls under the algebraic polynomial category. So I have a slower over a faster, right? Radicals is slower than my polynomial. Slower over a faster, it's always going to result in 0. My denominator is growing at a faster rate, even though this looks really large, but as we go towards infinity, eventually this x squared is going to overtake. And once it overtakes this value, this overall fraction is going to get smaller towards 0. All right, number 12, we're approaching infinity. Numerator and denominator, there's no, if we try to compare degrees, it doesn't fit, right? Because this is not, we don't have a degree for this. So we got to compare our, identify the family of function. Numerator, right? If the variable is sitting in the exponent, we call it the exponential category, exponential function. So you got an exponential function over a polynomial. So exponential over a polynomial, we got a faster over a slower. It has to be one of these two categories. And the way we test, we choose a number in the direction that we're traveling towards. Plug in 100 so that we can choose between our two options. I just want to pick the highest exponent here. So here I get a negative. Denominator, I get a positive. Negative over positive is negative. So when you're comparing, when you're doing growth rates, there's only two options. It's either 0 or plus or minus infinity. Okay, thanks everyone. I'll see you guys tomorrow. we'll do test review.
Thank you, Mr. Yang.
Thank you. Thanks, guys. Have a great day.
Thank you, Mr. Yang.
Thank you. Have a good day, guys.
Thank you.
Bye.
Bye.
Have a
Thank
good day,
you.
Mr.
Bye.
Yang.
Thank you. Thank you.